So we'll just kind of give some vignettes on each one. To start off with, we recently lost a beloved GSOC member, Bev Vogt. She has left us, and I believe that this is the first of my talks that I've ever given that she's going to miss, or she's missing. I owe Bev a lot. She was always very kind to me, editing my papers and the maps that I did with under the auspices of GSOC. Very kind to me during her tenure. We're going to miss her. All right, in a career like mine of several decades, you encounter individuals that are very impressive for their intellect, their diligence, hard work, and just sheer creativity. Then years later, after your retirement, now years after that, their character continues to inspire you as a lifetime of your own experience helps to further appreciate their accomplishments. They get better with time. Recognizing those people as individuals and noting their achievements is an effort to repay them for the enormous gifts that they made. What follows this evening is a score, a little bit more actually, of a few of my personal favorites. There are others, along with very brief descriptions of some of their contributions. So we'll start out with James Dwight Dana. I'll always put the date they were born. This is not a eulogy, so I won't put in the date that they died, but the date, born in 1813. And Dana wrote the Dana's Manual of Mineralogy. Most geologists who were educated in the United States before the 1970s used his manual, Dana's Manual of Mineralogy, because that was usually the first course. That was the first course you took, mineralogy as a major. Anybody could take the beginning geology course, but if you took mineralogy, it usually meant you were on the road to being a major. His Manual of Mineralogy, 126 years later, over a century and a quarter later, it's in its 23rd edition. It's still in print. It's cranking along. It's easy to read. The book is particularly easy to read, and it covers all aspects of minerals, including their utility and a lot about the crystallography. So I always admired his work, and I'll put him here at first. Dana has a special tie. Dr. Dana has a special tie to Oregon in that he went on what we call the Wilkes expedition in 1841. They sent a group of explorers and scientists out to Oregon from Washington, D.C. to assess some of the landscape in 1841, some of the resources like timber and minerals, if any. And he was the scientist. It was like a trip to Mars in a way, but they got here and they went down almost as far south as Eugene in the Willamette Valley to look at resources. And I always delight in quoting to my friends in Bend his comments, the comments Dana made about the Willamette Valley resources, the Western Oregon. He said that the Oregon Coast Range and the Cascades are well timbered. They're very richly timbered and usable timberly. He said the Willamette Valley is very fertile and it will be nice for farming and grazing. But he said Eastern Oregon, east of the Cascades, the interior, what he called the interior, was good for little or nothing. Anyway, so he might be my first slide. Let's see. The second individual that I've always admired when I took petrography and petrology is Dr. Norman L. Bowen. He was every geologist, every educated geologist knows Bowen's reaction series. He was a Canadian geologist, and he unlocked the mystery of felsic and mafic silicates. By using the experimental petrology and thin sections. He sat down and he literally created minerals. He cooked them and made minerals, crystallized minerals, And for that, he used the Washington, D.C. Carnegie Institute for Science laboratories, and that was between 1912 and 1937. During my 2 terms at the National Science Foundation in Washington, D.C., I was able to several times go by his lab. If I had to see somebody over there, they still maintained the same lab that he had. And you can see that firsthand. Going from his conclusions, going from high temperature here, from high temperature to low temperature, minerals pass through an interesting transition from being iron magnesium rich or mafic rich with a simple molecular structure to the low temperature minerals around 500 to 600 degrees, which are felsic, silica rich, and with a very complex lattice system. And in between, we get micas or sheet-like structures in between. So this Y-shaped diagram, the discontinuous, continuous series here going all the way from olivine down to quartz is part of every geologist's early education. Dr. Bowen is, without question, he's regarded as probably the greatest petrologist of the 20th century. Really quite a remarkable individual. All right, another one, getting back there a little bit, William Davis is responsible for what we call the Davissian system of landscapes, the Davissian system of landscapes. Dr. Davis, William Morris Davis, was a geomorphologist, and he came up with a kind of an elegant model of landscape evolution that proceeded from a youthful stage here with subdued or almost flat uplands, small discharge streams with waterfalls, rapids, and V-shaped canyons. And those mature into what we call the state of, from a youth to a maturity state, which has maximum relief. The distance from the top of the hills to the bottom of the canyons is a maximum. They're very rugged. The much larger streams just beginning to meander, No meanders up here. These just begin to meander. And we finally wind up with time. The topography winds up in what we call an old age stage setting with subdued lowlands again, almost like flat like the youth, but they've eroded down, subdued lowlands, and a complex braided meandering streams, oxbows, oxbow lakes, wide floodplains, and an enormous discharge on the river itself. He gave us this, and it was easy to learn this. One of my first beginning geology courses, I got attached to Dr. Davis at the Davissian system. Hydrogeologists, people who study surface water, and geomorphologists have since that time constructed a quite different nomenclature and model based on the number of stream tributaries. The number of tributaries increases with the age of the topography. And this new nomenclature is called stream order. But frankly, old habits die hard. And if you say to any geologist that a stream valley is in old age, a practicing geologist mentally immediately calls up a picture of oxbows, wide looping meanders, and channel bars. So the Davissian system prevails regardless of the stream order system because it is so easy and elegant to understand. All right, I know these are getting kind of old age here. We'll get a little more modern a little bit later on. Carl Alfred von Zeil, 1839, a German paleontologist, obviously. In 1893, he published a handbook of paleontology in 5 volume sets that pictured and described the known fossil record at that time. In each of my education venues, as Sheila said, Oklahoma, California, and Michigan, I was repeatedly referred to Zeil's work for its superbly illustrated and detailed pictures. Then, in the course of my master's degree and PhD, when I was required to pass language exams to get my degrees, I was asked to translate German for my language requirement and was handed a random passages. They handed more than once, random passages from Zeil. Books I knew backwards and forward. I could have done it with my eyes closed. Zeil's tomes also provided many of the drawings of fossils for books I have written. I can't draw nearly as well as they did. So I owe him a kind of debt of gratitude. All right, we get to Inge Lehmann, a Danish seismologist, and I was introduced to the science of geophysics as practiced by Dr. Lehmann when I took geophysics at Michigan State. When they worked out the anatomy of the Earth from the crust down to the inner core, it was a top-down process beginning. So the first thing they discovered was what we call the moho, the moho discontinuity at the base of the crust. And then moving on down, in 1909, Lehmann came up with the discovery of the inner core. What she discovered was that the inner core, the outer core was liquid, iron, nickel, and the inner core was solid. That was the configuration she came up with. When I took geophysics in 1965 in Michigan, my instructor walked the class through the mathematics, which analyzed the speed, reflection, and refraction of P waves that Dr. Lehmann used in her work. It was really incredible. You had to have a calculus book in one hand and then a textbook in the other hand to understand it. Dr. Lehmann lived to be 104 years old. After she retired in 1953, she traveled to America for a time to continue her research with such luminaries as Frank Press, who was Jimmy Carter's science and technology advisor, and Maurice Ewing at Columbia University. So she was in a good heavyweight crowd there. A very remarkable person. All right, get a little bit further down. We go to an individual, Manly Natalin, born in 1906. And I will remind you that we have this concept in geology, uniformitarianism. The present is the key to the past. Manly Natalin, or Nat as we called him, was a devotee of that. If you wanted to understand fossils, if you wanted to understand geologic things, look at modern specimens first. Have some knowledge of the biology. I met Dr. Natalin in 1962 when he was working in downtown Los Angeles and for Atlantic Richfield Oil. And I was a graduate student at Riverside, California. In the early 1930s, he was an exploration geologist working in Southern California. At that time, foraminifera, and you see a bunch of foraminifera here. This is these white ones here are very shallow water forms. There's a deep water form there, a couple of deep water forms up here. But the foraminifera were the primary tool or weapon at that time for correlating strata in the Los Angeles basin. But Natalin he soon realized that most of the correlations that were being made were of environments and not time. In other words, two identical microfossil faunas that you could pick out usually represented, if they were identical, they represented a specific environmental setting, but they weren't necessarily the same age. So they thought they were correlating time, but they weren't. They were correlating environments, which is not time. So in order to form a better picture of the stratigraphy and structure of the Los Angeles basin, he made a sampling transect across the continental shelf of Los Angeles from San Pedro over to Santa Catalina Island. And he took and examined several hundred bottom samples. And then he did the paleontology law, laid all these things out. And he was able to distinguish between estuarine, inner shelf, middle shelf, and outer shelf he could see exactly where these things are. Most of these things in the LA basin are still living today offshore. So he could find them out here and he could lay out the depth exactly. Okay. So he went as far from the estuary right down into the bottom, way off the edge of the continental shelf. There's no trough out there, but he got in very deep water. It was classic uniformitarianism. The present is the key to the past. Classic example of utilization of that. Now he could look at a microfossil fauna and assign a very specific depth. What this did was it enabled him to build a detailed picture of the Los Angeles basin along with its oil-bearing layers. His sampling system was more remarkable. It was a kind of constructed together winch system powered by a surplus motorcycle engine. And he was operating on a very small boat, taking sightings on the land to see where he was as he did this transect. And the whole budget for this whole project, which actually earned him a PhD at University of California, Los Angeles, was only $300, far cry from what we have today. Really a remarkable individual. One of his minions later on, when I got to Oregon, she and her husband came to Oregon and she took a master's degree from me. So we kind of went full circle there. Another micropaleontologist that I still admire was Orville Bandy, born in 1917. He was raised in Oregon, and so I have a tie here. He took his bachelor's degree and his master's at Oregon State under Earl Packard. At that time, Joseph Cushman was regarded as the father of American micropaleontology, but he only did foraminiferae, didn't do anything else. Bandy did his PhD work at Indiana under Jesse Galloway. But early on, Bandy realized that while bottom-dwelling foraminifera were, as Natalin said, were good for recognizing paleo environments and settings, the average duration of a species of bottom-dwelling or benthonic foraminifera is 20 million years. Planktonic species, as you see here, these little balls, each one of these is a separate species. Planktonic species, they have the average range length of a species is only 5 million years, so they're much better for age-dating rocks for correlation. Furthermore, these planktonic or planktic forms were, as part of the plankton, were good for worldwide correlations that the benthonic foraminifera could not do. But they were far more difficult to identify. I found that out at Riverside, and it culminated in my doctoral degree. Most of Dr. Bandy's career was spent as professor at the University of Southern California, which is where I knew him. And he is best known for his close ties to the oil industry. A really remarkable paleontologist. All right, we get to Oregon, and we have here Earl Packard, born in 1885. Getting my cue card out now, that's better. Dr. Packard replaced Dr. Condon at the U of O after a short gap after the latter's death. After Thomas Condon's death, there was a space, and then Dr. Packard came. He was educated at Berkeley, and the University of California, Berkeley, and he was a member of what they called the association. It was formed by the Berkeley professor John C. Merriam, very famous individual, and it included the association in very, very interesting group, such luminaries as Chester Stock, Q, Buwalda, Bruce Clark, and so forth. On page 294 of my first edition of Oregon Fossils, there's a picture of the association sitting on the steps of the paleontology laboratory. As Oregon's sole paleontologist for years, Dr. Packard collected and described a variety of fossils, much bigger variety than you'd expect a paleontologist to do today. It included things like Mesozoic ammonites you see here, which are about 2 to 6 inches across from eastern Oregon. But he also had whales and reptiles, mostly turtles, from Miocene locations in the Coast Range. So he really had a very diverse range of things he was publishing on. While Packard loved Eugene, in 1932, all sciences by act of the legislature were moved to Corvallis, where he was made Dean of Science. Needless to say, he was less than pleased with both his new assignment and the venue. He didn't really like when he retired, he moved back down south to California. Another paleontologist, Heinrich Lawrenstein, 1912, born in 1912, educated in Germany in the 1920s and 30s. He was able to hear Alfred Wegener lecture on continental drift on several occasions. He told me that. It's quite interesting. As a Jewish individual, he was denied his PhD by the Nazi government at that time, just before World War II. He traveled to the United States and he acquired a doctorate at the University of Chicago. In 1962, I was going out regularly on the research vessel Valero 4 run by University of Southern California. I also had an association with Dr. Bandy. We were doing work off Southern California. Dr. Lawrenstein was on several of the cruises. We almost always shared meals and sometimes a cabin. He is known mainly for his work in what we call biomineralization, or how animals and plants utilize minerals in their shells and tissue. A couple of his really profound discoveries. We have here these bullet-shaped fossils, which is the internal skeleton of a primitive squid-like mollusk. It looks like a squid, but not quite the same, a belemnite, and they're made out of aragonite. And what he did when they got using the isotope oxygen 18 and the atom 16, the ratio oxygen 18 and 16 will give you a pretty accurate reading if you can collect that from the shell on the temperature of the water when the animal was growing at that time. And he took one of these belemnites and he just ground down through it, they grow like an onion, layers on the outside. And he ground down through and he took layer upon layer, and he was able to show, to our astonishment, now these things are like 180 million years old, but he was able to show that the belemnite he had lived about 5 years, and it had a migration from very cold water to very warm water on an annual basis. He was able to tell that. So he was getting a lot more information than we usually do for most fossils. Another triumph was this little guy down here, which is a mollusk we call a chitin. It's a primitive little chitin. It looks like a trilobite, but it's got 8 little parts of a shell here. And this thing grazes on the bottom. It's a bottom dweller, and here's the grazing pattern. He grinds into the rock and he grazes and he eats algae that are embedded in the grains of the rock, all right? So Dr. Lawrenstein said, well, this guy the shell of this thing is made out of calcium carbonate, which only has a hardness of 3. And he's cutting into rocks here with a hardness of 4, 5, and 6, some of the sandstone. And what he discovered was that these little rascals are using magnetite like a carbide-studded tire, like a winter tire, to graze. So these marks here are made by the radula of this little chitin, but he's using these carbide-like magnetite studs. One of the things that the biggest gift he ever gave me, he said, if you go on and you go to academics, he said, in your job interviews, when you do a job interview, don't ever delete taxonomy and classification. He said, nobody cares about taxonomy and classification. They're interested in what you can do with these fossils, but not so much how you classify them. And I took that to note. When I came to Oregon, I had basically just finished a taxonomic thesis on foraminifera, but I was working on a an aspect of calcite where the calcium carbonate is contaminated. The calcium is substituted with magnesium and strontium. And in very cold water, we get pure calcium carbonate. But in tropical water, we get, this is just about any animal you can name, we get often strontium and magnesium substituted in the in the calcite lattice, because they're all about the same atomic ionic radius. So I gave that talk at Eugene, where they had a lot of geochemists. They couldn't hire me fast enough. It was a good thing to say, because really not very many people really care about taxonomy. At least that's my opinion. All right, so we go to here to Martin Glazener, born in 1906. He was born in Bohemia in the Austro-Hungarian Empire, a micropaleontologist, educated in Vienna and also in Moscow. He took a doctorate in law in 1929 in Vienna, and he did a PhD there in geology and paleontology in 1931. He worked in Moscow in 1930s in the oil industry. And in the 40s, he immigrated to New Zealand, and then he worked also in Australia and New Guinea. In 1945, he published a textbook, Principles of Micropaleontology, which differed from almost all micropaleontology texts in that it considered everything that comes up as microfossils. There's all manner of things, bits and pieces. If you have to use a microscope, it's a microfossil. Most textbooks up until that time were actually mainly foraminifera or ostracods or something of conodonts or something like that. It was one of the first texts to treat everything, all known types of microfossils, plants and animals. He's best known, however, for his publication of what we call the Ediacara fauna of Australia. These little pieces in here, anywhere from 2 to 3 inches across. They're a soft body animal. They're characterized by this segmentation, all these segmentation everywhere. You start looking, they're all carefully segmented. They're flexible, and they have been regarded, he regarded them, Glazener regarded these as the first known multi-celled animals, metazoans. It's not really a surprise that they assigned this find to be described by micropaleontologists, because we look at all manner of things, obscure parts and pieces of unknown affinity. And this was really puzzling when he found it, but he decided it's a soft-bodied animal, but it represents the first known metazoan animals. And it goes back more than 575 million years in the past. They lived a short time, and it's called the Ediacara fauna. Very important. All right, we follow that with a little bit more on Ediacara. Another German, Adolph Zylberberg, born in 1925, grew up in Germany, and he worked under Schindewolf. Schindewolf was a very famous German paleontologist at the University of Tübingen. He later was an adjunct, Adolph was an adjunct at Yale University in 1987. He worked in what I consider the most difficult aspect of paleontology, and that is trace fossils. They're also called ichnofossils, tracks and trails. All these are tracks and trails. Like there, this is a track left by a fish swimming, that's going back and forth to the swim. This is a Ediacaran fauna, which is another contribution. But he did a very perceptive man. His work, tracks and trails, and he can tell you all kinds of things about the organism just by the track and trail or burrow that it left behind. All right. Zylberberg turned his eye on, he began looking at the Ediacara fauna, and he said, he said, these early metazoans had a soft body, and the way they got their shape, this is a picture of the organism, he's a couple inches across, but if you magnify this thing, the way they get their shape, they have a series of panels that they inflate with seawater. It looks like a quilted pattern, or not unlike a air mattress. So he figured that out. And then he also said they disappeared almost very quickly. They were just a very short time, but it was the first Metazoan. And he explained their rapid disappearance because it was coeval with the appearance of jawed mammals. And his comment was that Ediacarans, his summary was that they were utterly edible. For a jawed animal, it was duck soup. When he rolled this synthesis out, very famous, he rolled this out at a national meeting in Indianapolis that I was at, and he rolled this whole explanation out of how these things work and what they meant. There was, at the end of the talk, it would seem like an eternity, a long moment of complete silence in the room. And then followed by an absolute thunderous applause. There must have been 700 of us in the room. A really remarkable perceptive paleontologist working in a difficult field, and he made a real contribution. Adolph Zylberberg. All right, we'll move up a little bit higher to Marie Tharp and Bruce Hazen. They worked at Columbia University in New York. Hazen had made several important discoveries working on the ocean floors in submersibles. Among those, he actually was able to track a turbidity current, which is moving across the ocean floor at a little under 50 miles an hour. But as a team, their most profound achievement was a series of maps of the world's ocean floors. Beginning in the 1950s, in the early 50s, they assembled data from dozens and dozens of military and oceanographic efforts from scores of sources. Their maps showed fault scarps thousands of miles long. This is one of their maps, came out 57, of the Atlantic Ocean floor. Incredible detail. They collated all this data from other nations all over the world and began to create these maps with amazing detail. You could see fault scarps that were thousands of miles long, deep canyons and trenches, longer than anything on the continent. But the crown jewel was when they were able to show a mid-ocean volcanic ridge, the mid-Atlantic ridge here coming down there, connecting up with the Indian Ocean, connecting up with the East Pacific rise here. A chain of subsea volcanoes bigger than anything we had, nothing even close to it on land, that connected all three oceans, and it extended for 50,000 miles, enough to go around the Earth twice, a continuous chain. They all hooked up, kind of like the stitching on a baseball. This 1977 map laid to rest most of the lingering doubts about the plate tectonics synthesis. This was really kind of brought it all home. Tharp Hazen's map of the ocean floors. Another remarkable achievement. All right, to introduce the next character, it's necessary to go back to 1872 to 1876, the voyage of the British ship HMS Challenger. It was exploration. They started out here in England. They went out through the Caribbean, back down like this. They followed a path through all three of the major oceans for 3 years. They took dozens and dozens of plankton tows, they caught fish, and they sampled shallow and deep ocean floors, sounded the shallow and deep ocean floors in all three major oceans. One of the samples they took was right here. The Lesser Antilles are right in here, a volcanic chain. And just a little bit to the east of the Lesser Antilles is Barbados Island. The rocks in Barbados are rich in microfossils called radiolaria. I'll show a picture to you in a minute. And these fossils in Barbados were 50 million years old, and they were washed off the island by the streams to commingle with the skeletons of living radiolaria that these people on the Challenger were collecting. So what we have is essentially a massive contamination from Barbados here into the modern ocean there. We're contaminating Eocene-aged radiolaria with modern radiolaria. When the Challenger returned to England in 1876, the man assigned to describe them was this individual. He was assigned to describe the radiolarian samples, name them and draw pictures of them, microfossils. And this individual, Ernst Hegel, 1895, was a would-be artist, sometime artist, and scientific illustrator. Hegel, to most of you, is known for his ontogeny recapitulates phylogeny thesis, where he imagined, he's got pictures of fetal animals. He's got a human fetus here, a rabbit, a cat, a hog, and so forth. These are all, he has a kind of a fetal, a series of fetal pictures or drawings. And he imagined that vertebrate animals undergo a sort of metamorphosis from fish to amphibian to reptile to mammal in their prenatal development. Okay. His drawings of radiolaria, this is his work on some biological specimens, but he kind of made it arty. He made designs with these things. But the radiolaria, these are the radiolaria that he sketched. But a lot of these are kind of imaginary. There is like an organism kind of like this, but they don't have these appendage. He imagined and he sort of attached things on which he thought looked kind of neat. So he wasn't exactly faking him. I think he was having a really, really serious identity crisis when he published this material. But he had contaminated samples of Eocene and modern radiolaria. So the word went out that because radiolaria have such long stratigraphic ranges from the Eocene to the recent, which is a cool 50 million years, they're useless as chronologic indicators. Okay, they were judged to be unusable as a geologic time, as a time marker. All right. Hegel's not somebody I particularly admire. I just had to talk about him in order to talk about William Riedel, 1927, just before I was born. He was a professor at Scripps Institute of Oceanography. He was a radiolarian, and they're mostly oceanic forms. And the first thing he did, he recognized the error that Hegel had made in sampling, and he corrected that. And immediately that meant radiolaria became a very powerful tool for accurately age dating oceanic sediments. What you have to know is that radiolaria, the skeleton, it's a single cell organism. Actually, it's a predator. You can see these on the head of a pin. You can't see any detail unless you're young, but their skeleton is opaline silica, so they do not dissolve. They will dissolve eventually, but they do not dissolve easily, and usually they're preserved. So we get whole lineages of these things. It was the first time anywhere we could look at fossil lineages and see a progenitor over here, which evolves into this, which evolves into this, which evolves into this. This is an evolutionary line, but they just pick out some end members. Distinguishing this guy from this guy is really hard. Moreover, distinguishing this species from this is also hard. So what he was able to show was that evolution, at least the way the radiolarians are telling the story, is a painfully slow process, like watching paint dry. And if you can see every single specimen, there are very few punctuations in the process. A real contribution. He gave us a weapon to do oceanographic studies that has never been excelled. This was a major step forward just in time for ocean drilling, the deep sea drilling project to prove continental or plate tectonics. William Riedel. All right, the next person we have is Tanya Atwood. She was our speaker a while back, born in 1942. And my admiration from her was just on her credentials and just her raw intellect. I don't think I've ever met her peer. She was enrolled at MIT, Massachusetts Institute of Technology in 1960. She got her PhD at Berkeley in geophysics in 1965. And she was later a professor at MIT for a while. She wound up at the University of California, Santa Barbara. She's now retired from there. And while the rest of us in the 1960s were monkeying around working out the Atlantic, the spreading system in the Atlantic, she was already over here in the Pacific. Here's Oregon, there's Washington there, Oregon down in here. And what she was able to do was she was able to connect the East Pacific Rise. You can see it coming up here in the Sea of Cortez. She was able to connect the East Pacific Rise, a spreading center, with the spreading center we have offshore, the Juan de Fuca Ridge, and they are tied together by the San Andreas Fault. Really remarkable. Tanya was educated during an interval when women were regarded or considered as bad luck at sea. And we see her here in this picture as the first woman to pilot the research submersible Alvin. So she came a long way, a real pioneer, and probably one of the most clever geologists I've ever known. Tanya Atwood. All right, we go then to another individual I knew, Dr. Lester King, born in 1907. In London, he immigrated to New Zealand early in his career, and most of his career was spent in South Africa in Durban, where I took a sabbatical. In the 1950s, he was a Southern Hemisphere geologist. So in the 1950s, he went on several tours all over the Northern Hemisphere, lecturing on continental drift. And he called it not plate tectonics. It was not, they didn't have that yet, continental drift. And in the Southern Hemisphere, he saw 4 incredibly powerful arguments for an ancient supercontinent we call Gondwana. Those arguments were, first, the puzzle fit. These continents fit together like a jigsaw puzzle, almost exactly. Really remarkable fit. The puzzle fit. All 5 continents, Africa, South America, Australia, India, and Antarctica, the 5 continents of Gondwana fit together like a puzzle. He also noticed, or people had noticed, that there a series of plants and animals shown here, reptiles, mammal-like reptile, and some plants on here, they coexisted on different parts of Gondwana. Well, today, these things are literally tens of thousands of miles, no, thousands of miles apart. So it's unlikely, that was a good argument that this was once a single landmass, because these animals occur on several of these continents at once. They weren't swimming animals. He also noticed what we call the stratigraphy. No matter where you are, whether you're in South Africa or parts of South America, Australia, India, or Antarctica, you have a layer system. The South Africans call the lower part the Duica tillite. It's a glacial tillite. On top of that is another layer, a little younger, the Eka sandstones. Above the Eka is another sandstone, here in yellow called the Beaufort, and then finally the Stormberg. No matter where you go in Gondwana, you find the same sequence, Duica, Eka, Beaufort, and Stormberg. Well, the likelihood of that happening when these things are thousands of miles apart is low, too low to believe. Right? The fourth argument is probably in many ways the most powerful. He could see, and Wegener showed us this, that they had structures in South America, faults, basins, fold mountains, that you could see them when they stop, and you can pick them up over here to Africa, which is separated today by the South Atlantic Oceans. Same thing here in Antarctica and Australia. He could see structures across these things, like tearing a newspaper, so that the sentence begins on one page and it's on the other page. You can read it. Pretty powerful evidence to support what they, at that time, they called continental drift. I took a sabbatical leave to South Africa in 1973, and Dr. King and I often dwelled over coffee on my slow acceptance of plate tectonics. I didn't think on quite the same level he did, but I was one of those geologists that was completely converted from a non-drifting world to a drifting world because of evidence I saw on the ocean floor. Lester King. All right, we get here to Hal Williams, also known as Willie. Born in Liverpool, England, he is regarded as the father of modern volcanology. In spite of that, he took virtually no formal training in volcanology. So all of his ideas, which are correct, were through his observations in the field. He's a real field geologist. He was a professor at the University of California, Berkeley, and he retired to take up residence for a period of time before his demise in Eugene, Oregon. He is best known, as I said, for his synthesis of Crater Lake as a collapsed caldera, shown here, shown looking back toward the east. Willie was a captivating lecturer and a wonderful colleague during his short tenure at the U of O, a really remarkable individual. Hal Williams. All right, then we get to another paleontologist, which is Bob Bocker, born in 1945. And he's wearing his trademark red shirt. He's got a dinosaur hand here. He's wearing his trademark red shirt. He was a Yale PhD under John Ostrom, Dr. Ostrom. For a time, he taught anatomy at Johns Hopkins. But his contribution was he was able to demonstrate that dinosaurs were warm-blooded and also closer related to birds, genetically related to birds and warm-blooded. Interesting thing, just a kind of a short story about Bob. He was a consultant to Spielberg's movie Jurassic Park. And when they were making the movie, they wanted a monster to chase these kids around the kitchen, if you remember that scene. And they couldn't agree. Bocker said, no, not this one. And then Spielberg picked one out. Well, Spielberg grabbed the dinosaur book and he started flipping through it and he landed on a page and he said, there, he pointed with his finger and said, there's my dinosaur. It's called Velociraptor. And Bob said, no, you can't use that because that dinosaur is as big as a chicken and it's not going to threaten anybody, let alone a couple of kids. And so Spielberg responded by saying, you know what, scale it up. Well, he said, what do you mean scale? He said, scale it up, make it big. I want it to be about 7 to 8 feet tall, fierce. I want to chase these kids around with this monster. So they did, they scaled the thing up. Then Bob told me this story about so this is a phony, as a fake, they scaled up a chicken-sized dinosaur into something as big as a camel. And about a week before the movie came out, somebody dug up a velociraptor, which was the same size as the one in the movie. And to that, Bob said, you know, after that happened, when somebody dug up a dinosaur just before the movie came out, I began to think, you know, maybe there is something to being a Jew. There maybe is something to this Jewishness. If you ask 10 paleontologists about Dr. Bocker, 10 of them would tell you that he is probably one of the most innovative scientists they've ever known. Quite an individual. Get down here to another woman, Anita Harris. Dr. Harris is a specialist in a microfossil called a conodont. And you see one here. These are conodonts mounted on the head of a pin. There's several types. What we call a cone conodont is like a horn. If you can see the head of a pin, you can see these things. A cone conodont, platform conodont, bar and blade conodont, the 4 kinds. Here is a conodont taken at 2. This is on a penny. This is on a penny. So if you can read the numbers on a penny, and you're sober and conscious, you can see conodonts. You can't see much detail, but these things are extinct microfossils. They existed on this earth for about 350 million years old, and they are fantastic guide fossils. They evolve rapidly, and they're not that hard to identify. You're obviously looking at a piece of some animal or plant, but we weren't sure what they were until about 1983. We had no idea what they were, but they're a part of the thing. All right. Anita Harris, working for the United States Geological Survey, one of the things she noticed that conodonts ranged in color. Some of them are dark black, and then they get lighter. They go from a dark black color to a amber, to a tea, to a clear. They get lighter. They go up there. And she realized at that point that what you were looking at is the history of the rock that had entombed these things, how much heat it had endured. So these conodont, and essentially by its color, the pigmentation of the color, tells you the thermal history of the rock. All right, we call that thermal maturity. What is that important for? When you're drilling a well if you're doing oil exploration, the first thing they'll ask you before they spud the hole in, they'll say, what's your target? Where is this oil? Where's it coming from? What's the source of it? What is the source rock? Where is it going to be drilled? We're going to get it out of it. And they also always want to know, what is the thermal maturity? Because if it's down here, you get conodonts that are black, the rock has been cooked and there's no oil or gas in it. If it's up in here, it hasn't been cooked enough, but if it's in here, 50 to 90 degrees, then you can get oil. So in other words, you have to cook an oil, you have to cook these plant tissues to get them to convert to petroleum. You have to know the thermal maturity before you start drilling wells to look for this. Then Anita published a couple of papers on this. It was really sensational, but she did an interesting thing. She gave a series of, this is a pick slide. There's just slides. Somebody mounted these things on microfossils on a slide. You can see how big they are. She's just put them on here. She made pick slides that showed this variation in temperature from very warm to almost cool up in here. And then she gave those slides to paleontologists worldwide to sort of promote her discovery and also enable them to do thermal maturity just at a glance. Another remarkable paleontologist, really remarkable. All right, we wind up here close to it by a little, not a geologist at all, but an astronomer, Carl Sagan. Most of you know who he was, born in 1934. He was an astronomer. He worked in Harvard and then Cornell for a while. As a geologist and paleontologist, I myself have always been, and I'm still intimidated by the vastness of space, of the universe, and geologic time or deep time. Both those things, I never really got my arm around them. I did my work, I'm a professional, but space, the size of space, the massiveness, and the immensity of deep time always bothered me. Sagan was able to explain it pretty well. He could talk about things. I always admired that. I wish I could lecture like that. But he was able to explain these, or he would explain why this is all right. In addition to explaining space and so forth, he also wrote extensively on the potential for us discovering extraterrestrial life. One of the things he did was he predicted that our first encounter with an extraterrestrial would not be a little green man. It would be fossil microbes or protozoa that occurred. You'd see it as trace fossils. All right, an organism leaves a lot more trace fossils than the shell it's living in. But he predicted that a micropaleontologist would be the one that discovered these things. I always thought that was kind of interesting. Carl Sagan. And finally, we get down here to Michael Crichton, 1942, born in Chicago, raised in Long Island, New York. he demonstrated incredible skill and imagination as an author. He was educated at Harvard Medical School, but never practiced medicine. Although he was trained as a doctor, there is a very strong thread of geology and paleontology that runs through many of his stories, all fiction. Every paleontologist on this planet owes Michael Crichton a huge debt, as his novel Jurassic Park and its numerous sequels blossomed into popular culture and ignited terrific interest, a renaissance of interest in the earth sciences and paleontology. He's got a picture here on time, which is like getting your face on the cover of Rolling Stone, I guess. Thank you for your attention.
Good. Okay, let's see, do we have any questions? I didn't see any questions come through the chat.
Make a comment?
Bill, do you want to stop? Can you stop screen sharing?
Oh, wait a minute. Wait a minute. I can't find it.
Just hover towards the bottom and it'll say stop share.
Oh, I see it. Okay, right there. All right.
Okay. And then we want to see your picture too. We want to see you. There you go. Okay, good. Okay, I'm not seeing any questions in the chat box, but people do have, one did come through.
Yeah, Carol was asking, why did you not include Darwin?
Oh, I knew that would happen. Oh, why don't you ask why I didn't include Einstein or Dr. Condon? Everybody has their own list. And Darwin would have been kind of passé. I'll probably give to this audience a talk that compares Charles Darwin to Wallace, the person who looked at the marsupials in Australia, because they both kind of co-discovered evolution in a sense. But Wallace was working in Australia and Condon, of course, was working in the Galapagos. But I could have, any number of people I could have talked about, but I just picked the ones I had.
Remember, as a disclaimer, I said this is not an exhaustive list. There's so many more people he could have put in. Yeah, good. Okay, Charlie Montrose, you had a comment. Hi, Charlie. You want to unmute yourself?
I got my bachelor's in '79, and yet they're still arguing about continental drift and plate tectonics, looking for evidence.
No, there's a lot of people that still don't buy into it completely.
Trump?
It's no longer a theory. I think it's fact. But when I was working at the National Science Foundation as program officer to run the ocean drilling program, the Glomar Challenger, some of our Russian scientists who were on board taking samples, they believed in a kind of a modified continental drift theory, but it was not plate tectonics. They hadn't swallowed that yet.
Mm-hmm.
Thank you.
Look at his background. Wait, stay up a minute. That background, go back to it. Can you get the background again?
Which background?
Charlie's.
That is a pic. That's a cover. I use that for a cover of a book. The first book I wrote, Liz and I wrote on Oregon fossils. And
It was a horned gopher, Mylogallus heteri.
Yeah, it's a rodent that has these pretty substantial horns, and the front is about as big as an alley cat and the huge claws. It's a digging animal. And my colleague at the University of Oregon now, who partially replaced me, Samantha Hopkins, her specialty is, of course, fossil rodents, and she knows all about those. But they're really a strange little animal, quite remarkable.
But we're trying, Paul Lamb, he's been trying to get a laser map of these Mylogallus hatcherii, so we can make it everyone can have their own mascot of that. But we can never could find anyone who would have a laser 3D map of a Mylogallus hatcherii to make our own. Supposedly, the people out at the John Day Museum, I've seen these things there. Whoops, where are they? Wrong finger. Okay, there we go. So they have them there, but we can never get the people to get us a 3D print of this animal so we can make our own copy. It could be the mascot of GSOC.
You might get one. You might get one from Samantha Hopkins at the U of O. She might have one, or know where to get one.
All right. Well, how do we contact her, or can you contact her?
Just go to the. She's on. You can get her. I don't have a phone number for her, but she's in the Cascade Hall there. I could contact her and ask her.
Great, thank you. I have my own Mylogallus just for myself.
Yeah. Other questions?
Can I make a comment?
Yes.
Every time I listen to Dr. Orr, I get more excited about paleontology because I've discovered something new
Yeah.
about the usefulness of paleontology. I go like, holy cow, that's what it's for. You were talking about Michael Crichton, and the way that you talked about him, that's the way I feel about you.
Well, I always thought, in fact, I told the governor this. I got appointed to a state board of geology, and I told Dr. Kitzhaber that the fact I was paid, I was retired at that time, the fact I was paid for 30 years to do paleontology and geology was a borderline criminal act. And he said, well, you're retired now. It's a little late to tell me. But I did. I think I put in my time. And I think that the state did okay, but I probably came out ahead. I was quite grateful I was able to do this for the state.
Isn't that the one that he asked you what you did for a living and you said you were an entertainer?
Yeah, I did. Yeah, it's true.
Okay. Okay, well, I'm getting some, we have some good comments in the chat box. So, and somebody that was with us and already left out said that he would very much liked your presentation. So many scientists and a diverse spectrum of information. And this person said that you have sparked my interest to return to college and complete my undergraduate degree after 40 years.
Yeah, well, tell him small bills are accepted, no consecutive serial numbers. Old bills are best.
Okay, will do. Good.
Hi, Carol.
Okay. With that, I think we can turn off the recording now, probably, right? Unless anybody else has any questions.